Hi. In this lesson, we need to talk about how we go from magma or lava, like you can see in these images, into igneous rock. This is a process of freezing, of crystallization, of turning from a liquid to a solid as the magma cools. This is key in understanding igneous rocks. Now, it can be tricky to look at the processes involved in the crystallization of magma. We can see the images of lava flows cooling, solidifying, crystallizing. But if we're trying to understand how rocks might cool beneath the surface, perhaps at slower rates, we need to look at an experiment. The experiment we can use for this is one using a liquid called salol and dropping this onto microscope slides. And if we drop this on microscope slides that are cold, we'll see very rapid crystallization. And if it's on a warm slide, very slow crystallization. What I'd like you to do now is press pause and watch the salol experiment video. Once you've done that, you can answer the question on page 4 of your Theme 5 booklet. Okay then, having watched that video, let's look at some results. If we drop the salol on a warm slide, we can see crystals that look a little like this. You can see these crystals are really quite large, over 1 centimetre across. Now, if we drop the same liquid on a microscope slide that's been in a freezer, so it's much colder, we see a mass of crystals that are much, much smaller. The ones in this particular example are maybe 1 or 2 millimeters across. So there's clearly a link between the speed at which magma cools and the size of crystals. Where we have a magma cooling slowly, we'll have larger, coarser crystals. Where a magma cools quickly, say at the surface, or particularly if it's erupted into water or into ice, it'll cool very quickly and we end up with very fine crystals. So, let's go back to the table, the classification of igneous rocks table on page 3. Now, there are some details to fill in, perhaps from last time, about the types of magma, how granite is formed from silicic magma, because it contains quartz, a lot of silica. Basalt is formed from mafic magma, lots of iron and magnesium in that particular magma. In between the two, we have andesite, which is intermediate in composition. And finally, peridotite, which has got even more iron and magnesium in than basalt, and therefore is ultramafic. There is a difference in density of these rocks as well, because of the minerals that are in them. These are some of the figures we'd expect. Make sure you add these to your table as well. Now, this lesson really is about crystallization and the speed at which igneous rocks crystallize and the effect that has then on the texture, on the size of crystals. So, for our coarse igneous rocks, like granite, like peridotite, the rate of cooling there is going to be very slow. For medium-sized rocks, it's moderate. For fine crystals, that cooling is very rapid. And for obsidian, where we don't see any crystals at all, it's extremely rapid, probably instantaneous cooling. Make sure you have these details on your table, on your classification, which needs to be complete. Okay, let's have a look at two rocks. We have specimen S and specimen Y. Now, normally we would do a practical on this, but what we're going to do today, I'm going to describe these rocks, these rock specimens to you, and I'd then like you to have a go at answering the questions on page 5. So all parts of question 3. So watch this description and then have a go at answering those questions. These are the two specimens that we need to look at in terms of their texture. For an igneous rock, the texture is the size of the crystals that make up the rock and the relationship between those crystals. So we have two specimens here. We have specimen S and specimen Y. Let's look at them in turn. Let's start with specimen S. So this is specimen S. We can see that there are 4 different minerals within this rock. We have these pink glassy minerals, several of these scattered through the rock. We see a fairly large quantity of this sort of grey, colourless mineral that looks like little shards of glass within the rock. We see a white glassy mineral, a white vitreous mineral. You can just about see there are 2 planes of cleavage for that one. And then there's a small amount of this shiny, black, flaky mineral sort of dotted throughout the rock. Now when we look at the texture of this rock, we can see that most of the rock is made up of the grey, white and black minerals. If we measure the size of these, they do vary in size a little bit, but we can see the grey minerals there are often about 3 millimeters. The white minerals maybe a little bit more, 4 to 5, maybe even 6 millimeters across. And then the small number of black minerals are about 1 millimeter. Perhaps most striking, though, are these pink crystals. The pink crystals, you can see, are really quite rectangular in shape. They're quite a regular shape compared to the rest of the rock. You'll see as well that these crystals are considerably larger than the rest of the crystals. So these pink crystals are, well, that smallest one there is about 15 millimeters across. We have one here that's at least 25 millimeters, although we can't see the full extent of it because it's broken. We have one here on the other side that's nearly 30 millimeters. So the crystals in this rock vary in size. Now that's going to be a result of how this magma crystallized, how it froze. So you need to have a look at the questions in your book and to get you thinking about how this rock would actually have crystallized. Specimen Y looks very, very different. Specimen Y is much darker in colour. It almost looks black. And the crystals are a lot less obvious to see. The minerals in this rock are predominantly a black glassy mineral. There's also a small amount of a white glassy mineral in here as well. And it's a little bit hard to see, but you can just about catch a hint of a green colour. So there's a small amount of a green glassy mineral in this rock as well. So the composition of this rock must be very different from specimen S. The crystals in this rock, we can see, are much, much smaller than in specimen S. We can see that there are definitely crystals within this rock. It doesn't have sort of the shiny appearance of a glass. So it is crystalline. And these crystals are comfortably less than 1 millimetre across. You'll notice as well that there are no larger crystals within this rock. All these crystals appear to be approximately the same size. So we can see we now have two very, very different rocks that we need to try and understand how they formed. Okay then. We should now have a full set of answers to question 3. It's clear that from those two specimens that the rate of cooling changes the nature of those rocks. It changes what those rocks are like. I'm going to go through the answers to those questions in the next lesson. I'll see you then.